In this video, we will talk about how to find absolute maximum and absolute minimum of a given graph. Absolute max and absolute min are sometimes called global max and global min. These are points where in a graph, it's the highest point and the lowest point. So the highest point is called the absolute max and the lowest point of the graph is called absolute min. So for example, if you have a graph, some kind of graph, it's not this function, it's some, let's just say some function, and you are given some kind of a interval so that you're only considering the portion of the graph inside some given interval. And let's say the graph that you get after restricting is like this portion of the graph. Let's just say here, from here to there, okay? Now, in here you see that the highest point of the graph is this one, that's the absolute max. And the lowest point is absolute min. And we actually see that it has some relationship with the relative max and relative min that we learned, because this absolute max also happens to be higher than the nearby points, and it's also the interior of a given interval. So it's an inside point. In that case, the absolute max has to be at a relative maximum. Okay. This one is also a relative minimum. But this is not the lowest. This is. Okay. So being a relative minimum or relative maximum doesn't necessarily mean it's an absolute maximum or absolute minimum, but the other way around is kind of true. You can see that if you have an absolute maximum or absolute minimum inside a given interval, just like this, when you have an absolute maximum inside a given interval, then it has to be a relative maximum. Or in case of absolute minimum, it has to be relative minimum. Now here is another case. Absolute minimum happens here. This is at the boundary points, and for boundary points, you can't say, we can't talk about one side of the graph, so you can't talk about relative max and relative min because you only have one side. Only this portion of the graph is valid. See, only this portion is valid. So at the boundary points, you may have an absolute max or absolute minimum, like this case. Maybe thinking about the following two examples might help. So if you had a function like this, and in this case, it's absolute maximum happens inside the domain, and it's a relative maximum. In here, this is the absolute minimum, and that happens at the boundaries. How about this one? In this case, this is the lowest point, that's the absolute minimum, and because it's inside the domain, it's also relative minimum. And I guess if these are same height, then they're both absolute maximum. Okay. After drawing a few graphs and looking at the examples, you can come up with the following conclusion. And this is actually a theorem. Any absolute extremum happens at a point of relative extremum or at the boundary points. So this theorem is saying if you have an extremum inside the domain, it has to be one of the relative extremum, or if it's not, then it has to be at the boundary points. Now, let's think about how this theorem could help us. It means that the upshot of this theorem is that when we're trying to figure out absolute extremum, we either have to consider just 2 points. Number one, the boundaries, maybe value at the boundaries, okay? And number two, it has to be relative extremum inside. But we also know that relative extremum can only happen at critical points, right? So this happens only at critical points, critical numbers, right? So we need to find the value at critical numbers. Okay, and once we check the value at the boundaries and value at the critical numbers, and then because the absolute extremum can only happen at these places, the highest value becomes the absolute maximum, and the lowest value becomes the absolute minimum. Okay, so just if you have boundaries and if you have values of critical numbers, and then among these values, the highest value will be the absolute maximum, and the lowest value will be absolute minimum. There is, however, one slight danger to this simplification. It's that sometimes absolute maximum and absolute minimum might not exist, and this is the second case. So let's go and read this question. Here we are given a quadratic function, and we have to find the absolute max or minimum here. We know that this is a parabola opening up, and from negative infinity to infinity we have this graph. So what do we know? We see that it has a relative absolute minimum. It must have the absolute minimum at the vertex, right? Somewhere. We don't know. We'll figure it out in a moment. But look at what happens when you try to find the absolute maximum. It goes up forever, right? So it doesn't have an absolute maximum. It only has an absolute minimum. So so certainly you need to think about the graph, and from the graph, if you know that there must be an absolute maximum, then you can just look at the boundaries and critical numbers and choose the highest value, and that will be the absolute maximum. If you also know that it must have an absolute minimum, then you look at the boundaries and critical numbers, and you look at the lowest value. That will be the absolute minimum. Okay, so with this theorem helping us, let's try to solve this question. All right, first of all, we will think about the graph of y equal to x squared plus 4x plus 2. We know that it has a point where it curves. Those of you who still remember the formula negative b over 2a, x equals to negative b over 2a, you can use this to figure out the vertex. Well, you don't have to remember this, because we know that at the vertex you have a horizontal tangent line. So if you differentiate, you should be getting 0. So let's differentiate and set it equal to 0, so that you get negative 2 as your critical number, right? Actually, this is a critical number because the derivative is equal to 0. This is the only critical number. Okay, now let's try to evaluate the function at the boundaries. Okay, here's a boundary, negative 4. What's f of negative 4? That's negative 4 squared is 16. 4 times negative 4 is negative 16 plus 2, so it's equal to 2. How about f of negative 2? F of negative 2 is 4 minus 8 plus 2, so it's negative 2. And then f of 0 is equal to just 2. Okay. So among these, which one is the lowest? Negative 2, right? So this must be absolute minimum. Oh, but wait. Before we make any conclusions, we should first think about the graph. The graph is, here is negative 4. The value is 2. At negative 2, the value is negative 2, and then at 0 you're up to 2 again. So it's like the graph that we have on this A is you start from 2, goes down and turns back and goes up, and the difference between the left point and the right point is because 0 is not included, you have an open circle here, whereas on the left you have a closed circle here. Okay, so from this graph, we definitely see that absolute minimum is the lowest, right? So it does have, we definitely see that there is the absolute minimum, right? So because we know that it has an absolute minimum, the value that gives us the lowest value must be the absolute minimum. Now, for the highest point, we see that this point is actually highest. This is also the highest, but the problem with 0 is not included. So this is the absolute maximum. Okay. So for A, you have to say the answer is absolute max is negative 4, comma 2. And absolute min is negative 2, comma negative 2. Okay. How about in the case when you allow for all wheels, so that you get infinitely large values, because you can plug in infinity to here to get infinity as the value. Okay, so in that case, as I explained in the previous slide, you don't have an absolute maximum, so you only have an absolute minimum. So in part B, no absolute max, whereas you have absolute minimum as negative 2, comma negative 2.